CLion, a cross-platform IDE for C and C++. Download now.
This session is probably by some measure going to be the lightest of the day, notwithstanding your efforts earlier, Dom. I'm possibly in with the week. And so we're hopefully just going to have a little bit of fun and a bit of chat and relax a bit before the lightning talks, which of course are a high-stress session for Pete over there. So if having nice time doesn't appeal, then do please go. I shan't be in the slightest bit offended. So what are we going to do? We are going to talk about some magic software. So there are lots of things in software that seem kind of amazing, right? Even we work in software all day, every day, right? We're familiar with lots of, all aspects of it. But things like operating systems, for most of us, they're pretty amazing, right? Compilers and interpreters, windowing systems are pretty fantastic. I can't find the reference, couldn't find the reference. If Kevin was here, he'd give it to me. That I'm going to confidently state that the comprehension limit, right, the most code you can hold in your head is about 10,000 lines, right? Unix version 6, 1975, was about 10,000 lines. So that was the last time you could hold the whole of an operating system in your head, right? So there are device drivers bigger than that. Operating systems so big, right? So big, so incredible that they work at all. Right? Although, for many of us, and perhaps for many of our less technical friends, operating systems are less a source of wonder than of irritation. Okay, so let's set that aside. Sat-navs. Sat-navs are pretty cool. I mean, you need specialist hardware for a sat-nav, which most of us have got now. But here's a sat-nav in action. So it's getting real-time GPS updates from the sky, so it knows the direction that you're going. Sorry, this is a bit of a fuzzy screenshot. But anyway, you can see the gist of it here. You're heading in that direction. You know from the GPS the direction you're going. You know the speed you're going because you've got the underlying mapping data. You know how far it is to the next turn. You know which direction that turn is. You know how far there is left to go. You can work that out from the map data. You know how fast you're going, and you know how much of this you've already done, so you can give an estimated arrival time. This is quite funky, but it's also quite pedestrian. None of us are amazed by this anymore, right? But they are pretty cool. Lots of game stuff is pretty amazing. And I'm not just talking about graphics rendering. Anyone know what this game is? This is a game of Dominion, right? And it's a deck building game. So you have a hand of cards at the bottom here. And the aim of the game is to get lots of these green cards, these victory cards on this side. And you do that by playing out these treasure cards to buy these action cards from the middle of the table here, right? And these action cards all have different rules. So the rules of the game change according to the cards you have in your hand. And there are hundreds of these different action cards, because once, it's a game you can go to the shops and buy, and it comes in a lovely big box with lots of big cards, and it's sold really well, so there's an expansion set, In fact, you can stack them up like this high, hundreds of these cards. So probably the combination that you're playing, especially on this rather good version that you can get on your tablet, is probably, no one's ever seen that before. It's a unique combination. And the game, the computer opponents, are really good. They're really good. And the thing is, if you replay this set, chances are it'll play it in a different way. It's not just kind of, we're going to pour this into a SAT solver and the optimal path drops out. It plays it in a different, we play the same cards in a different way, and it seems to play in response to things that you do. So it might act differently if you buy a different combination of cards. It's really, really good. I haven't got a clue how it works. It's really good. I love it. It's great. This, you might have read an article about this recently. This is a more mundane, but still fascinating, because this calculation at the top here is actually quite hard for computers to do. Hans Bohm of garbage collection fame spent months and months and months basically developing whole new branches of numerical computing to do that sum. Right? That's quite amazing. It's quite cool. But these are all quite large topics, especially the game one, because I don't know how that works. Right? They're all quite large topics. And we can't cover an operating system, and we can't even cover a calculator in the time available to us today. Because, well, I'm not Ken Thompson. I mean, I haven't even got the beard for Ken Thompson. You know, he could have done it, I can't. But about this time last year, I was, poking around on my phone, insulting my kids or something. I don't know what I was doing. And my keyboard, Microsoft SwiftKey, suddenly popped up a little notification asking me if I wanted to turn on an AI assistant to boost my productivity and unlock my creativity, which is a little bit presumptuous. Now, I said no, because how much productivity boosting do you need for a WhatsApp message? But, we're all familiar with our phone keyboards, right? And they serve a couple of purposes. The first one is to kind of spell check the thing that we're typing now, the thing that we're typing. And then the next thing they do is suggest the word that we might want to type next. So they're doing predictive text. They're generating text. And you might have occasionally played that game where you just accept the suggestions, right? And it looks almost like a sentence that I would write, because it's been taken from sentences that I did write. Okay? Kendrick's car, actually quite good. I don't know what's wrong with that. I talk to lots of different people on WhatsApp. That's all I'm going to say. So the first time I encountered this kind of next word prediction was either the end of 1991 or the start of 1992. My wife, I could make a joke of my wife at the time. My wife, still my wife. And will continue to be, I hope. Anyway, my wife, she was training to be a teacher, and the school had a computer, which was not as common then as it is now, and they had some software, and they were having some trouble with it. And even though I was an electronics engineer, she said, "Oh, Jez knows about computers, he'll come and help you." And I didn't know about computers, but I went to help them. And it was some copy protection thing, it's not important. Anyway, the software was essentially a word processor, but it was intended to help kids who had writing difficulties, specific learning difficulties to do with writing. So dysgraphia, or dyslexia, or dyspraxia, or any one of a number of other writing problems. And it did word completion and next word prediction, which I hadn't ever seen before, and it was really quite spooky. Right? It was really quite spooky, and it really struck me. And the fact that I can remember it now. Well, obviously it had quite a strong impression on me. And so here now, 35 years later, was my soft keyboard on my phone rebranding next word prediction as AI assistance, right? And suggesting that this technology was in the same bucket as the ChatGPTs and the Claudes, and that these were hard problems that were best left to the big brains in Silicon Valley and Redmond and wherever. Now, I don't know about you, and with respect to Anastasia and to probably you, Bryce, I'm not sure our general experience of AI assistance has been magical, necessarily. So perhaps some of these guys are overselling what they've got. So if we could do next word prediction on one of these, which is, Roger? Thank you very much. BBC Master System, which was probably 40 years, or 5 years old back then, it's 40 years old now. If we could do it on then, could I recreate the magic, I thought. Could I recreate the magic? In an hour. Now, I don't know, I'm not quite sure where I came up with this, but I just sat down to watch an FIH Pro League hockey match, right? And international hockey matches are 60 minutes long. This one went longer. I think it was Spain, India. It was 2-2 draw, and it went to penalty shuffles, and it went to 8-7. It was really exciting. It went a bit longer, but 60 minutes, notionally 60 minutes, right? A couple of minutes between the quarters, 10 minutes at halftime. But anyway, we're in that kind of hour, 90 minutes ballpark. Next Pro League hockey, 7th of June. Got Spain, Argentina doubleheader, which should be great. And then Netherlands, Australia women, really good. Netherlands, India in the men at the Wagner Stadium in Amstelveen. If you're free, go along, it'll be really cheap, you'll have a great time. I think Spain are going to win both games. Argentina are in a rebuilding phase. Dutch women, they're never rebuilding. They're always, never bet against them. They'll win. I think India will beat the Dutch men, and that will cause ructions. It's going to be great. So anyway, I had a hockey distraction. No such distraction today, unless I start, looking forward again. So anyway, I did do it in an hour. So all the code I'm going to show you today, there isn't much code, but all the code I'm going to show you today is in JavaScript. Okay, so so my first language is C++. I mean, it's not, but you know what I mean when I say that, right? And because of that, and you've probably had these conversations as well, sometimes you talk to people who work in Python or PHP or whatever, and they go, oh, that bit twiddling, it's all a bit low level for me. I'm not really up to that. And you think, well, I guess you are. And also you meet C++ programmers who are a little bit sneery about the PHP programmers and things, right? Those guys, set them aside. But I find it really infuriating, actually, that there are these members of our community who've taken that, who are victims of that snobbery, who've taken it on themselves, right? I think it's really bad. We're not on some rarefied mountaintop. Programming's programming. This is the most, malleable medium that we work in, right? So if you can do anything in software. So if you can do it in JavaScript, because I was going to pitch this to a different customer with a very different audience, and they rejected it. But anyway, so I'm going to do this in JavaScript. If we can do magic stuff in JavaScript, then we can do it in anything. And it does fit on a slide better. So you can vote with your feet. So when I say magic software, I don't necessarily mean that it's unknown or difficult or particularly deep, just that the effect that it had was kind of, whoa, right? And this next word prediction was, whoa, thing for me back then. And sometimes just to implement this software, all you need is like half an idea and just to bang your head against it for a bit. So the half a clue that I had was Markov chain. Is this the half a clue that everybody else has? Maybe. So I kind of vaguely knew what it was, and I knew it was something to do with probability. So I messaged my son Daniel, who's doing a PhD in stochastic epidemiology, which I think is just rolling dice with viruses. Okay? And I said, remind me what a Markov chain is. Now, those dads in the room will see this as a classic dad maneuver, right? I'm pretending I know what it is, and it's just flipped my mind. And he is not playing ball, right? Now, he knows, most of you can guess, I didn't do GCSEs because they hadn't been invented. So I said, so remind me. I didn't do GCSEs. And it was at this point, I turned to other sources. So, a Markov chain is a stochastic process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So stochastic process is mathematician talk for random. It's a random process. The sequence of events means that a thing happens and then another thing happens and then another thing happens. Probability of each event depends only on the state obtained in the previous event. It's quite a formal way of saying it doesn't matter how we got here. We're here, these are our possible futures. The future does not depend on the past. Okay? It's a memoryless process. It doesn't matter how we got here. It's called a Markov chain after a chap called Andrei Markov, who was a Russian mathematician, did a lot of stochastic process work. I think he was born in 1856, died just after the First World War. So this is quite a well-established piece of mathematics. Here's a little state transition diagram. Here's a Markov process. We can start over here on state A, and we can choose a random number, and that might take us to state B, and we can choose a random number, and that might take us to state C, probably will, quite a high probability there, and so on. And we can just sort of move around this state diagram, and you'll see the total, I haven't made this easy for myself, the total of the outgoing probabilities adds up to 1. So we've got a 0.4 here and a 0.4 there. And even if we're staying, in this case, in the same place, that's still got a probability. That's still a transition to the same state, okay? So you think, well, what good's this for? What's this for then? Macroeconomics did a lot of statistical or probabilistic simulations in macroeconomics. Despite this, they still cling to the idea of the rational market, but they run a lot of stochastic simulations. They have, apparently, Markov chains have apparently been used to model the interaction between state actors. We may have to review that in the light of recent events, but apparently it's been done. They have applications in algorithmic music generation. In baseball analytics, apparently, I thought that was really well. I thought the whole Moneyball thing had taken the randomness out of baseball. That was one of the criticisms of modern baseball, is that it's also predictable, but apparently not. And of course, since you've all read the synopsis, you can use Markov chains for algorithmic text generation. So how do we apply this to our text generation? So here's our state transition. If we strip that down, ding, if I knew graph is better, my little boxes wouldn't have jumped around there. But life's too short. So what if we associate state A with a word? Ding, hello. And state B, hello there, hello there. State C, with everybody. And then state D, with the Brian Koenig approved word, world. Okay? So we can run some simulations. We can start at hello, or we can pick a random number. Fran, pick a random number. Okay, that's more than half, is it? Because if we go 1 to 10, that's more than half. Hello, everybody. And we start again. We go hello. Done. There. See? Easy. We've got a greetings generator. Okay? So that's it. We can all finish. I'd buy you all a drink now, but I can't afford it in this hotel. So, but what's the missing step here? How I just said, we'll put hello at state A and world at state B and things. Where does that come from? How do we know what the words are, and how do we know what the probabilities are? Okay. If we put this in code, the little example I just showed you in code, it looks like this. We create a chain from our chain package, Markov chain. We add the words. And that will give us a little data structure that looks maybe something like this. So we've seen the word hello, and it was followed by the word world once, the word there twice, and by everyone once. And that looks a little bit, if you squint and turn it sort of sideways, looks a little bit like our state transition diagram. And indeed, if we ask it to kind of predict some things, maybe 10, maybe you need more than 10 just to get the numbers quite, but it's coming out. That looks plausible, right? This is as minimal as you can get with these sort of 4 words. We have one starting word, and all these, and I've just asked for one more word. Okay, that's as minimal as you can get. And we barely even have any code. So this is my chain class. This is what we're making the chain. We've got an add method. That hash up there, everyone comfortable with a hash in JavaScript? It means private. Yeah. We've got private members now in JavaScript. Ha ha ha! Yeah. Yeah. That means private. A map is a map. A map is a map like a C++ map. Okay? So we add a token, a word, and the following word, and we say, well, is it already in there? Or if it isn't, then we make our little follower object, and then we pop it in the map, and then, you can see this. This is all unexpected. This is all as you'd expect, right? We're going to add things into our map as the words occur, and then we're going to add the followers. And then when we predict, we say, well, I'm starting with the word hello, so I get the hello thing out, and then I'm going to select one of them according to my random number. So the followers thing is a list. That's what those square brackets are. And we say, is it already in the list? And if it isn't, then we pop it in. And if it is, then we just bump its count. If we've seen it again, pop, bump. And then when we select, we kind of convert. This is just what I did at the time. So it's probably not the best, right? But you can add up the total number that you've seen of your following words, which in this case is going to be 4. And then we just, weight that by our random number, and it kind of it's a really bad way of doing the probability, but it works, okay? I'm looking at this now, and I'm looking at the programmers in this room, and they're going, oh, I should have reworked this some more. But this is the deal. This is the thing that I wrote in the evening while I was watching hockey. It's fine, right? I vibed it with the hockey. There we are. This is what Harmonpreet does to your code. There we are. And then this is the follower, which is just the thing that comes afterwards. So we've got the token and the number of times you've seen it, token and the count. Okay? Easy peasy. This, everyone comfortable with that? With the get? That's a property. It's a read-only property. Aha, haven't got those in C++. That's a win for JavaScript. There we go. That code, that's all fine, right? It's all what you would have, it's like 60 lines, maybe. So, how do we make this more than just a greetings generator? More words. We need more words. We need, we'll come to that in a moment. We need some more words. We need a text corpus. A body of text. It's a technical term, it's a corpus. There are a number of well-known text corpuses. Corpus. There are a number of these, and generally, more formally, a text corpus is kind of large, for some value of large, and systematic. So they're trying to gather, using some system, some methodology for a particular time period, or for a geographic location, or for a specific demographic population, or some combination thereof. There is the corpus of London teenage speech, all right? Which is a set of samples of spoken English, was collected, I'm not sure of the ethics of this, it was collected by hidden microphone recording in 1993, some of the participants knew they were being recorded, but not all of them did, I don't think. Anyway, it's conversations between teenagers who are aged between 13 and 17 in London in 1993. It's a very specific text corpus, right? Sorry? Yeah, that's right. Yes, indeed. Ethics is the county next door. So it's about 500,000 words, all told, and contains 67 examples of the word bum, which I think is too low. That's my, I wasn't a teenager then, but it still feels a bit low. Anyway, so I didn't have access to any of those academic text corpuses. Nor did I really just want to go off and download random chunks of the internet. So I used a text corpus I was able to get full and unconditional permission to use, which was my Mastodon archive. So here it is. No, Jasper Carrot, it runs off the end. He did a static property. I'll tell you about this. Did a static property about 10 years ago, right? And he grew up in the area of Birmingham in which I live. My son, Harry, just seen him disappearing off, he was about 9, and you would not believe how much Moseley mixed school material, talking about school in the 50s, he loved it. He absolutely loved it. So Jasper Carrot, hugely down with the kids. So look at those, all of those. Everyone, a certified zinger. Look at that, pumpkin, blimey. So there are 2,384 scintillating lines here. As I said, Neil Gaiman there, I'll scroll past that one. Containing 46,576 individual words. And I've cleaned it up a bit to take out other people's handles and to remove the stronger swears, because one of my videos from a previous conference didn't get published. I won't tell you now why now, obviously, because I'm... So, and kind of looking at it sometimes, some of it does look like it was already created by a stochastic process. So, how do we build a chain from this? So here's one of the lines. This goes, phrase, to activate a sleeper agent. So we are going to take each, it's a little bit more sophisticated than breaking on spaces, but not much. So we're going to split this. We're going to take each pair of words, of tokens. I'm being a bit lax in my language. I've talked about words and I've talked about tokens. Strictly, we're talking about tokens because these things have, as far as the code's concerned, no meaning, right? They're just arbitrary collections of bytes. So we're going to take each one in turn. We're going to split it into... So this is my first word, is, and then the follower here will be this. And then that's going to slide along, and that's now our start word, and that's followed by the, and so on, and so on, and so on, all the way through, and we're going to generate a number of pairs from this. What are we going to do when we get to the end? What are we going to do about that question mark? You could, it doesn't matter, you can do what you like. I chose to have it as a separate token. You can put it in, I chose to have it as a separate token. It's slightly more sophisticated than splitting on white space, but not much. So I've got my input string at the top there, and I've put a little object around it just to do next has next. It makes the tokenizing slightly, makes the iteration along it slightly easier. Dropping any white space, gathering up things which look like they might be part of a word, yielding those. Sorry, this is the function star. Is that, are you familiar with that? It's a generator. If you know what Python generators are, it's the same, but with more brackets. It's actually the same, but with more brackets. This is a coroutine, essentially. So we're yielding up these values. We can iterate on it, and it yields up the values. So we've got something here, fall off the back, yield up the tokens, and then if we've got like other stuff, like punctuation, I'm yielding that as a separate, as a token of its own. And then I pop a little, oh, there it is, look, it's nothing. And then, where is it? There's my tokenizer in here, and I'm just popping them into a little 2-element array that I'm yielding up. Got a null at the start, null at the end, just to keep things neat. And then stuffing them into my chain, okay? So that gives us a data structure with something like this. So we've got is, followed by a, the indefinite article, 59 times, the definite article, 24 times, commas, 20 times, and so on. And 207 other things in that list is. Down to the bottom, well, we've got grateful nation once. Okay, there are 8,379 other tokens in this list, which seems like a lot. I think in English, I think most people have a working vocabulary, total vocabulary of about 10,000 words, and a working vocabulary somewhere less than that. So I talk a lot of nonsense, I think. And between them, so from the things on the left to the things on the right, there are approximately 35,000 state transitions. Okay, and I tried to get Graphics to draw that. And I left it, no, genuinely, I left it running for 12 days on my fastest machine And then I had to come here. And so I have a look. So this is all clear, right? We can read our source corpus, and we can generate a series of token pairs to be a big list of all the unique tokens that we encounter, together with the counts of all the things that follow them. And now we can take our starter word, hello, and use that to generate our next word. And then we can take the word that it's generated, and we can plug that back in. It's almost like recursion. And then we can take the word that generates and plug it back in and plug it back in for just an arbitrary length of time, which is what I was doing right at the beginning with the unflushable. Anyway, so we've recreated our little keyboard game. Okay, I just picked a dozen here. JavaScript standard library is not great, so I'm just buffering things up into a list and then splatting them all out, joined by a string at the end there. Printing's difficult. Would love a pipeline operator. If anyone's on the TCE 39, love a pipeline operator. Anyway. And that produced this, which, I mean, we know it's a random spray of words. And here we've got, obviously, we've got an HTML entity that's been broken up, the ampersand amp, and we've got, but what's little bits that look like phrases that might make sense, like a kerfuffle overhead, what kind of confusions, and, oh, clean. Everyone was wrong. Okay. But what's weird about this? It's like, what's going on here? And it turns out that hello is a really bad starter word for this particular text corpus. And this talk is the reason why. Because I talked on Mastodon quite a lot about writing the code and writing this talk, and I kept doing hello there, hello everyone. And so all the hellos are, whoop, there we are, hello, they're all in quotes. Hello, 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 right? So this is interesting, I think, and it's kind of unexpected. It's certainly unexpected to me, because hello seems like a perfectly normal word to start something off with, right? But this corpus, it has this quirk, this characteristic, because our little sliding window and our occurrence counts have captured something about this body of text, because we've built a model, right? It's a model of a particular dialect of English in a particular context, but it's captured something about that language. So, what do I do next? So this is the same code using the same text corpus, but rerun using a different seed word. So I'm using the now. And so this gives us some quite different results, which you'd expect now, given what I've told you about this text. And I think, I don't know, maybe it's better? Maybe it's better? Some candidates say that work, well, the first time in the spec in danger? Well, we've all been specs like that, I suppose. But anyway, what if we start with a different body of text? What if we start with one of the greatest novelists in the English language? We start with Pride and Prejudice. I haven't read it, but my computer has read it. And it's producing this little summary, so I've got the gist. I've got the gist. Now, Pride and Prejudice was published in 1813. So the word hello doesn't occur in it at all, right? People didn't say hello to each other in 1813. That's the invention of the telephone. But obviously the word the, classic English word, works splendidly. So here we are. The ladies always laughed heartily. Well, that's quite nice. We get these little islands, really, that from her brother's entrance of my, oh dear. Let's not dwell on that. But it's a very different feel, right? We've got a very different feel. There are about 3 times as many words in Pride and Prejudice than in my internet ramblings. So this is in terms it's a bigger model. I'm not quite sure how and what dimension it's bigger, but it's a bigger model. I don't know necessarily that it's more complex, because if I couldn't visualize the one, I certainly can't visualize this. I don't know whether Jane Austen's vocabulary is bigger than mine, or, I'm going to compare myself to Jane Austen. But could we, if we had, I didn't do this, but this is a fun thing to think about. If we had an unknown piece of text, an unknown body of text, could we compare it to Austen and the Higgins Mastodon corpus and say which one is it more like? That used to be, I think, quite an active area of research. Did Marlowe write Shakespeare? Did Marlowe write these little bits of Shakespeare? No, he didn't. But, is it more like Jez's Internet Outrage, or more like one of the greatest novelists in the English language? Here's some samples from a third corpus. Anyone want to have a stab? Exactly, there's a bit of a giveaway because the title's up. Right, you can read, good. So again, very different feel. I think perhaps not as distinctive. I do like this. He waved his brown, crumbly band. Well, I think that's quite evocative of something. So there's something also interesting about this as a corpus. Again, it's much bigger. It's about 3 times, I think. I've got it here somewhere. At 65,000 words. So it's 5 times as many as Pride and Prejudice, and getting on for 15 times as many words just in the length of the text as I had. But we've also changed another dimension. So my stuff on Mastodon was written over maybe 2 or 3 years. Pride and Prejudice written over sort of months. But these stories were written over a period of about 40 years. Okay? So the Study in Scarlet was published in 1887, and the last home story, or at least the last one that Conan Doyle wrote, was The Adventure of the Retired Colour Man. He made paints, I think. It was published in 1926. And so that's quite a long span of time, just in terms of the way people used language. Right? Conan Doyle was a jobbing writer. He would have wanted to stay, he would have naturally, I think, stayed current with current usage. So there's an evolution of the use of the language over that time. But also, we know that he wasn't actually, towards the end of his career, he wasn't super keen on writing homes. He tried at least twice to stop writing them. So there's probably a qualitative change over time. So this is a less distinct corpus in terms of those time frames and things that we've been thinking about before. So, and we think about Holmes as being very London-based, but he's forever on the train to the West Country or up north, vaguely up north somewhere in the home counties. So I think the whole thing is less distinct, geographically less distinct, it's temporally less distinct, it's linguistically less distinct. So, it's just a load of nonsense, right, these words. How could we make this model better? And for context, we are now deep into the 4th quarter of the match, right? It's 2-2, pressing for a win, right? It's getting pretty tense. I've spent the previous 3 quarters now writing those 60, 100 lines that I've shown you. How can we make this text generation better in about 7 minutes? How can we do that? Anyone? Okay.
3 words, that's it.
Oh, we'll come to that. Curse you. I thought the easiest thing I could do was improve the tokenization. And I said it's only slightly more involved than splitting on spaces, but we know, we have meta-knowledge about this line. We know it's written in English. And we know that up there, that capital letter denotes the start of a sentence. And this question mark denotes the end of a sentence. English has a grammar. We can't maybe write it down in EBNF, but it has a grammar, right? There's a generally agreed way in which we use English. So if we highlight the start and end of a sentence, we just add that as in JavaScript, we call it a symbol. So it's got an unpronounceable but unique name. We pop a little special token in at the start of the sentence, and we pop one in at the end, and then run our sliding window across it, but we include the start and the end there. Maybe that's going to change. Then we're going to know it's going to bias the model slightly. Some of these words occur here, and some of them occur there. And it feels like a tiny thing, right? It's like a tiny change. But it's actually quite big. We don't need a seed phrase anymore because we can go from the start of a sentence. We know the words that start a sentence. So we can just say, give me a sentence. And we can go until we see one of these end markers. So, I mean, it still wouldn't fool anybody, but that's better, isn't it? Right? It's better. It's radically better, right? I've done some little formatting changes so that, I'm not putting spaces. I'm trying to be a little bit clever about the spacing before punctuation, but that's in the presentation. That's not in the generation, right? This is better. Team sports, great smell. There is anyway. So, because this is I've only generated a single sentence, what about Miss Austin? Right? Her daughters seem to whisper. Semicolon. She loved the subclause. Jane Austen, semicolons all over the place, and I think if you'd included semicolons, this would be better again. See, her daughters seem to whisper, "Coaxed, Mr. Collins, been distinguished by reflection." I mean, these are plausible little snippets, maybe. It's just the whole is less. And also, of course, what's happening, every time we get to the end of a sentence and we start a new one, we're kind of resetting. So the sentences I haven't run on from one sentence to the other. We're kind of resetting each time. So it's significantly changed the output. Maybe it's made. I'm not going to put my hand in a pocket. I'll probably unplug the mic. That'll be bad. So it's maybe improved our output. And then, obviously, for completeness, here's our homes. You monster. Perfect. Perfect, you monster. What is steep my person of his agitation, but sorry if the hands up. I mean, you read some of those old Victorian novels, and they do have quite a tortured way with language. I'm still not. I'm not sure we'd spot this as derived from Holmes, but it is showing a bit more character. I mean, obviously, I ran this a few more times. I didn't run this once. I ran this a lot of times, and this is kind of typical. Oh yeah, but that could be any Holmes. That could be any Holmes. Anyway. That's because I put this in because it was better than the one I had in before, which didn't have Holmes. That's why I haven't. So there's more direct speech than Austin I think, in the Holmes, but there are fewer semicolons because he's a much punchier writer. He's writing for the magazines, right? He's a pulp novelist. It's an early pulp novelist. So what else might we do? And this is where we move into the largely theoretical portion of the talk, because now we're in the penalty shootout, okay? Penalty shootouts in hockey, it's not like a football thing where the ball is there and they're just whamming it at the goalkeeper, because you almost always score, because even I can fling that thing at 80 miles an hour, right? So what you do is you start on what we call the 23 and you dribble it in and you have a one-on-one with the keeper. And it's really good. The tactics of that have changed a lot. It used to be people scored regularly, then the keepers got really good, and now the strike, it's sort of swinging back again. Very, very exciting. Thoroughly recommend it. International hockey, it's great sport. On the telly, if you've got BT, it's on there. All right, anyway. So, how could we make this better? And this is where I'm willing to take suggestions from the audience, but not that one that you made, because I'm coming to that. So, we saw the effect of adding a little bit of additional information. I didn't change the underlying chain at all. I just put an extra little marker in. And we could extend that to speech. So we could put markers in at the start and end of speech. And perhaps other punctuation. I'm not sure if it's worth doing parentheses for English. but maybe we do something with commas, or maybe we do something with semicolons, right? They have a significance, and we could do something with them. And you could do that relatively simply. I think you could just put the start and end of speech markers in the chain, like we did with the start and the end of the sentence. But and then when you're generating the output, you could again use that kind of knowledge for like a meta state. So we're in speech, let's keep going until we hit the end of a speech mark. Or we're in speech and they've got to the end of a sentence, maybe we close the speech now. And so we're exploiting our knowledge of English to improve the output. And something that occurred to me actually while I was writing this was maybe you have two chains. Maybe speech is different from prose. So you have a chain that you're building, that you're training from your corpus. And when you encounter the start of direct speech, you start building a different chain. You switch chains and you run these dual chains. And then when you get to the end of speech, you switch back again. And then in your generation, you go from one to the other. I didn't do that, but that might be interesting, I think. That might be interesting. I think it would be interesting, and it would be quite straightforward. We could lean even harder into the structure of our language, and we could perhaps tag parts of speech. So we've got pronoun, verb, adjective. I was going to try and memorize this. Preposition, pronoun, noun, conjunction, pronoun, noun, verb, adjective. So we could tag our parts of speech. We could add additional information. We're still not adding meaning necessarily. We don't know what he means, but we know that he is a preposition and is in a different category to a verb or a noun. So if we had information like that, we could ensure that our algorithmically generated output lined up all its pronouns, for instance. So if we started with we were quiet in our ways. We could match our verbs. We were quiet in our ways, and our habits were regular. Okay, we could probably think of other ways we could use parts of speech in our text generation. If we wanted it more poetic, we just put more adjectives in. And if we wanted it to be kind of robotic, we'd take them all out, or we'd take all the pronouns out. Was quiet, is quiet, be quiet. Early parts of speech taggers were rule-based. There was a chap called Eric Brill, who pioneered this approach in the early 90s. And I worked for Berlitz around the turn of the most recent century. And we were using parts of speech tagging to extract what they called noun phrases from, I think they were photocopier service manuals. No, because what does, in an instruction, this is a specific example, what does replace the toner cartridge mean? Does it mean put back the toner cartridge? Or does it mean throw away the toner cartridge and put in a new one, right? So we were trying to pick out these ambiguous phrases to replace them with what they called a controlled vocabulary. So a vocabulary with a known meaning, you take out the ambiguous phrase, but to do that, you have to be able to identify these ambiguous phrases, and you need parts of speech tagging to do that. So this chap, Eric Brill, had a rules-based approach, and I think I used his code. More recent parts of speech taggers use a hidden Markov model. I did not know that. Hidden Markov model means you're not directly observing the output. There's some kind of, you're a remove from the output, but you're aware that there's an underlying stochastic process. We could stem, particularly if that's supported by parts of speech. And stemming means reducing the word to a stem, right? From explaining to explain, from worker to work, that kind of thing. So you can see how if you were building a Markov chain there, you would reduce the complexity of it, because every variation of the verb explaining would collapse onto one. But then you could perhaps use your other knowledge of your parts of speech and things then to expand that back out as you were generating. So you know that you've gone, or you could move things into different tenses. If you wanted something instructional, you could generate in a particular verb form. You must place the biscuit in the basket, right? Rather than you may wish to place the biscuit in the basket. You could have placed the biscuit. You know, we can then become more elaborate in our generation, theoretically, because the shootout's going on. So again, some of these stemming processes are stochastic because English, it's a large language. It's relatively easy in English because although English is large, it is reasonably regular. It's much more difficult in some other languages. Arabic apparently is very, very hard because of the nature of the language. So we can also continue to train. So training a model needn't be a one-off exercise where we gather up all this text and then just use it and use it and use it. Like I've been showing you here, we continue to train. We can add new entities to the chain, which is what our keyboards are doing as we type. They're adding new things in. So our word lists and our probabilities change. We can reinforce the model. So when our keyboard offers me these three choices and I take that one, maybe that's a better choice. So maybe I'm juggling the weights. I'm adjusting the weights to make that more likely. We're giving it a nudge. We could also perhaps add a time element. We may want to have a recency bias. Okay? If Elizabeth hadn't married Mr. Bennett, Mr. Darcy, would she want his name popping up in the autocomplete? Right? She'd probably want that to fade away over time. So we might add a recency bias to things that we've done, or we might fade out, or we might age out things, or we might do both. That might be quite fun. And I think we could do a lot of those things without changing that underlying Markov chain I showed you earlier. So we pre-process things on the way in, and we annotate, and then we kind of post-process on the way out. But I think the underlying chain is my supposition. I should have gone for like the whole of the, I don't know, the whole of the World Cup. That would have given me a fortnight, and then maybe I could have done this. But the bit in the middle would stay the same. If we're prepared to step away from that, there's all kinds of things that open up. So there's this idea of latent semantic analysis, which is the idea that words with similar meanings occur in similar contexts. You can build a kind of a state space of words, and related words cluster together. It doesn't mean they have the same meaning, but it means they have related meanings. So you might, family and son and father and daughter, they are related, but they occur in similar contexts, right? So you might be able to improve your generation like that. Anyway. Like I say, there's more than you can fit in one game of hockey. Natural language processing, fascinating topic to even to dabble. So let's do a little bit more. We've got some Jane Austen, lovely novel. We've got Holmes, and we've got my internet nonsense. What if we put them together into one big corpus, right? What would that look like? All right. I mean, it's just a big mess. More here is definitely not better, right? So my toots by themselves, remember, had 35,000 state transitions. So this is just unknowably complex. This runs in like 2 seconds on the laptop, right? And it is unknowably complex, right? And this is the most trivial text generation, right? It's unknowably complex. So some of these tokens, I said before, some of these tokens have a very small number of transitions, and others, the comma and whatnot, they have this very large number. So I think what's happening, as the size of the corpus increases, and the variation within the corpus as we're combining these very different texts, the fan out from like a comma just explodes, right? And it just gets bigger and bigger. And so the coherence of the output here is starting to fall off. But we've got these little islands of stability. So dwarfish chaparral bushes, is that from the Valley of Fear, I think? So you've got these little, and there's another one here, what is it? Yes. Quite possibly, quite possibly.
Because your total is actually underscore by line. Probably for that.
Yes, yes, I included underscores. Because I had this idea that I was going to do it with JavaScript as well, but that defeated me. I got just too many brackets. So quality here is very subjective, but I would say this is not good, okay? So if we go back to our earlier example, and I described how we moved the sliding window like two at a time, but we can widen that window without breaking the memorylessness property of the chain. And we can do what you suggested over here. So instead of building it with a single token, we can build it with like a pair of tokens here. So we'll say our token now becomes is this. It's followed by the, and then this the, followed by code, and so on and so on. So we have these sort of stronger starts, right, as we go through. And you go, oh, that seems better, doesn't it? I mean, I'm not sure what the reward function is here, right? I'm not sure, but it looks better. Elizabeth felt an anxiety on the JVM. Who amongst us has not felt an anxiety on the JVM, right? There's some proper sentences. I mean, they don't make sense, but there are some proper sentences in there. Although I think, we can see the kind of the transitions from, Austin to Mastodon and back. So if widening the window to 2 is better, what if we try more? What if we try 3 or 4, right? What about that? What do we make of this? Sometimes people are just speechless. I know nothing more of him than I have learned from him occasionally in the laboratory. This is directly from the sign of the 4 when Stanford is about to introduce Watson to Holmes. Jane met her with a smile of such sweet complacency, a glow of such happy expression, as sufficiently marked how well she was satisfied with the occurrences of the evening. Jane's had a great time. That's directly from Pride and Prejudice. Our model now is just regurgitating the source text, more or less wholesale. As we've widened the window and increased the length of that tuple, then the number of possibilities of the things that come after it has collapsed. So the width of 2 was kind of okay. It brought a certain amount of stability while still giving us variation. We had, I think, nothing more. Nothing more occurs in the home stories 40 times. So there's variation on that. But when we go to 4, we're regurgitating our training data to the world, right? So the quality has gone down. So with a less homogeneous data set, you can leak training data even on a window of 2. So that one there, hockey opposition have sacked off. That's directly because, I mean, I complain about the opposition a lot actually, but that's directly, and quite a large chunk of this, I mean, you imagine this is not a common phrase in written English. Amanda Grant's The Joy of Vegan Cooking Amanda Grant probably writes about it a lot. It's a very good book. Using 2 different date formats, there's the amazing and remarkable Monsieur Lyotard. Not a common phrase. Again, excellent book. Really, really good. So there are then we're picking out we're hitting these islands of stability, and it's regurgitating stuff from the source corpus. So inner, I think, is and where it switches here, that's the thing that's broken this part, and then we kicked off for something else, and it runs along until actually it got to the end of the sentence. There, we can always sort of pick the bones out of it. So yes, so inner occurs a lot, but then a very only occurs 6 times in this corpus, and then very different occurs once, and then once we've hit that very different, we're locked in. Okay. So, on the one hand, this is all just a bit of fun, right? I was just watching hockey and nurking about, right? So, because programming for money is great, right? But sometimes it's a little bit run-of-the-mill for most of us in this room. I know some of us I'm sorry, I'm not going to point at people and say you have an exciting career that I'd like to have myself. But with there, it can be a bit run-of-the-mill. We have a list of things in the database that we need to sort and filter and put on the screen over here. Great. And tomorrow, we have this list over here. So bunking off for a couple of hours and, putting on some sport or playing some Enigo Morricone or whatever it is, no one will notice. You'll have a bit of fun. And you can maybe do something that's really quite fun and magic and surprising, right? And you'll feel better for doing it. And on the other hand, and now I'm feeling very self-conscious, the title of this talk is obviously an allusion to the AI, I'm going to skip some of the words I've written here, business that's sort of swirling all around us. So even a tiny system, even a very, very tiny system here, can display surprising, it's not entirely convincing, but surprising behavior. And we've got, maybe 100 lines of code, but the model is literally beyond comprehension. It really is unknowable, right? And as we feed it more and more text, as the complexity increases, actually the quality of what we get out is degraded, it got worse. And then as we widened the window, it got better and it collapsed. And they were really quite sudden. The cutoffs were really quite sudden. And, I don't think it's unreasonable to think that larger, more inherently complex behavior will display even more surprising and even more convincing results. But perhaps as they get bigger and eat more of that text, perhaps they will also begin to degrade. But will it be as obvious as what we've seen here, right? And, it's not unknown for AI chatbots to go full on Nazi within a few hours. But what about the more subtle degradations, right? If we haven't noticed, does it mean that they haven't? Okay, and I think that's really going to be a very difficult question for all of us to, well, I'm not sure we can answer it, but I think it's quite a big question that we need to think about. So programming is like loads of fun, right? And we can reach out and we can explore these incredible problems really we can do it from the comfort of our own sofa on these, 10-year-old laptops, right? And for every little problem, there's like an infinity of solutions, right? Even tiny problems, there is an infinity of solutions that we can come up with. This like this multi-dimensional space that we can explore, right? But the things we build can have consequences, and the consequences are more difficult, or they're as potentially as manifold, but more difficult perhaps to quantify. So have lots of fun, but let's be careful. All right. So thank you all very much for your time and your attention and frankly, your indulgence. Thank you.